Hello and welcome to the introduction talk for the last lab of the spring term, which is about active filters. Two parts to the lab. In the first part we'll look at the basic design of some simple static active filters. That is, filters which have a frequency response which is fixed with time. And in the second part of the lab we'll look at tone controls, and we'll be building up the tone controls on the VAM board in this part of the lab. So, in the first part, we'll be investigating this particular type of active filter, known as a VCVS, or voltage-controlled voltage source filter. It has the advantage that you could get a wide range of different frequency characteristics without using any inductors. And as the slide says, inductors are large, expensive, non-linear, have large parasitic resistances, and are very difficult to incorporate in silicon integrated circuits. So usually a filter designer is happy to go quite a long way to design something which doesn't require the use of an inductor. We'll build up this filter in stages. First stage, the single stage RC filter. And we've seen this kind of thing before. You can analyze it using the potential divider equation. The output over the input would just be 1 over j omega c over r plus 1 over j omega c. Multiply top and bottom by j omega c to get the expression as the ratio of two polynomials. And we just end up with this. That has no zeros. It has one pole at minus 1 over RC. So if we were to plot its amplitude response on a Bode diagram, it would start off at 0 dB, because at low frequencies you can neglect this term with respect to the 1, so it just behaves like 1 over 1 or 1, which is 0 dB. It would carry on flat until it gets to the break frequency of the pole, which is 1 over RC, radians per second. And then it would head down at 20 dBs per decade from there. It's known as a low-pass filter because it allows low frequencies to pass through the filter without any attenuation. But at higher frequencies here, the waveforms are attenuated as they go through the filter. It reduces the high-frequency content, in other words. Right, so that's a single-stage RC filter. You can combine two of them and end up with a two-stage RC filter like that. And if you're interested, you could go through the derivation of that frequency response. It's not particularly difficult, it's just a bit time-consuming, but the result was in the lecture notes if you're interested in looking it up. I set a challenge in the lecture to see if anybody could prove that for this filter it is impossible to get a Q factor of greater than 1/2. I don't know if anyone has attempted it or even succeeded, but if you haven't, then do have a go. It's quite an interesting little puzzle. It does leave us with the problem, though. What do we do if we want our filter to have a Q factor of greater than 1/2, but we don't want to use inductors? Well, we'll get to that in a bit. The next slide just puts some gain at the end of this two-stage RC filter. So, still no resonance peak, we still have a Q factor which cannot be greater than 1/2, but now we have some gain as well, and we have the advantage that the output impedance of this filter is ideally 0. It's being driven from the output of an op-amp. You may remember that one of the properties of an ideal op-amp is that it has a 0 output resistance. Okay. We can make this into a much more interesting circuit if we take this capacitor here, disconnect it from ground, and connect it to the output of the op-amp instead. That gives us this circuit. And that's the only difference between this circuit and the previous circuit. We've just changed where this leg of this capacitor is connected to. You can go through the analysis of this. I think I went through the analysis of this in the lectures, and you can derive these expressions. We have a two-pole filter here. There's two capacitors, so normally that would give you two poles. The Q factor is given by this expression, and you might note that R1 plus R2 over R2 is just equal to 1 plus R1 over R2, and that is equal to the gain of this op-amp at low frequencies. So the Q factor could be simply expressed as 1 divided by 3 minus the gain at DC. And that allows you to make just about any Q factor you want, starting at 0.5 and getting higher. The minimum possible Q factor is now a half, because the minimum possible gain of a non-inverting amplifier like this is 1. So that just gives you Q equals 1 over 3 minus 1. That's the minimum value of Q, which is a half. But the maximum value of Q is unbounded. You can choose a DC gain to get just about any value of Q you want. And there's something even more interesting that happens with this circuit. What happens if your value of the gain at DC is set to 4? That would give you a Q factor of 1 minus 3 minus 4, in other words, minus 1. We have a circuit with a negative Q factor, which we haven't seen before. Now, you may like to think about what's going to happen if you have a negative Q factor of your circuit. And there's a couple of ways of thinking about this. One of them is to think in terms of this expression for the Q factor, which we haven't derived, but it expresses the Q factor in terms of the energy stored in a circuit divided by the energy dissipated per cycle. Now, in an electric circuit, the energy can be stored in the electric field in capacitors or in the magnetic field in inductors. Energy is also dissipated by any current flowing through a resistor. That will cause heat to be generated in the resistor, which counts as energy lost from the circuit. And the ratio of the energy stored in a circuit to the energy lost per cycle is another way of defining and determining the Q factor of that network. If you have a negative Q factor, then either you're storing a negative amount of energy or you're dissipating a negative amount of energy per cycle. And you might like to wonder what that means. You could also work out where the poles are. And if you do that, you'll find out that the poles of a circuit with a negative Q are, unlike any other pole that we've seen before, they're on the right-hand side of the imaginary axis on an argand diagram. Just about any other pole that we've seen or will see in the course of this module will be on the left-hand side of the argand diagram. But with a negative Q factor, if you work out what that means in terms of the poles, you'll find it means they're over here, on the right-hand side. And you might like to think about what that implies in terms of the behaviour of these poles. Once you've had a bit of a think about it, you can build the circuit, set it up with a negative value of Q, turn it on, and see what happens, and see if you were right. There are some supporting presets available in DASIM. They're under the Filters menu item. This is VCVS filter A, and if you set the variable resistor here to go between 1 and 40k, then you can change the Q factor, because the Q factor is determined by the gain. And you'll see that as I change the value of this resistor, the gain of the circuit is changing, the low frequency gain here is moving up. And I'm beginning to get a resonant peak here as my Q factor increases. As I go up to 40k, the Q factor would be, in theory, minus a half. And the simulator is saying that this would be the amplitude response in that case. Is it right? Well, I'll leave you to investigate that by building the circuit, switching it on, and seeing what it does in the real world. That's all for this one. Good luck.